Everybody, good morning. This is Chris McTaggart, your instructor for another edition of the Building Smart Energy Efficiency for Essentials for Modern Homes. Sponsored by DTE and Consumers Energy. I'm back, Taggart, your presenter for the day. We're just going to give it a couple of minutes so that we can see participants start to roll in. So just hold tight. And I appreciate we got a couple new folks who were not previously a part of this series. And so it's good to see people here attending the webinar series. Okay, well, I haven't given it a little bit of time. Again, rolling into today's webinar to attend it in real time, or if you want to go back and reference it, we are recording these sessions. They will be available through the program's website for reference once again. Today, we are continuing with our series focused on energy efficiency in modern homes. So what we're trying to do is take some of those best practices that we've probably known for some time, or at least we thought that we knew, and we're trying to kind of update what our knowledge is. What's really going on today. It's 2025. This whole building performance industry has been around for several decades, and I think a lot of people who've been in the industry for a while, they get taught a certain way, and it's always good to have a refresher for professional knowledge. Also, some people, maybe they are just now getting into the industry and they really want to understand, where do we stand today? What are the best practices today? And so today's lesson is going to be focused on the application of fenestration as part of a building envelope strategy for more energy efficient homes. So fenestration, that's talking about windows and doors and skylights, basically the opaque surfaces of our building that can allow opaque or translucent rather, surfaces that allow for us to see out to the outer world. They're a big part of living in homes, but they have some positives and potentially some not so positives when it comes to energy efficiency. So we're going to go ahead and kind of roll into this and talk about how does fenestration sort of fit within the context of modern energy efficient homes. So first and foremost, we're going to just talk again, a little bit of a quick reminder. What is the building envelope? And then when we talk about fenestration, what matters in terms of fenestration? What are we really looking at or considering when it comes to fenestration? And let me just tell you, this may seem like a boring topic. I know what an NFRC sticker is. I'll tell you what, there's a lot more to it than just the NFRC sticker. So we're going to be getting into that, really kind of in a more detailed fashion. Energy code, fenestration. So, what does the current Michigan energy code require as it pertains to fenestration? And then if we're taking the next step into above code programs, what do these programs require as it pertains to fenestration? And then we'll kind of do a wrap and go get prepared for next week. Okay, so again, I'm your instructor, Chris McTaggart. I am the co-owner and technical director of Building Efficiency Resources. We are a national ResNet home energy rating, quality assurance, and training provider. We work with raters in practically every state around in Detroit. And so I have a deep touchstone and affinity for what's going on here in Michigan. Grew up here in Metro Detroit and went to college at MSU. Don't hate me if you're a Wolverine fan. We're all in it together, but be closer to friends and family. And I'm very happy being back here in the state of Michigan, even though we're going through a major heat wave right now. Thankfully, I have done things to modernize my home for energy efficiency and installable in my home, thankfully. So when we're talking about the building envelope, again, you've attended the last couple ones, we're coming again, but it's important to understand the building envelope. You could call it the building shell, the building enclosure, pressure boundary, thermal enclosure, same deal. It is the boundary condition of our home that are being conditioned by heating and cooling systems to keep people comfortable within their homes. Is a six-sided box. There's a floor, is a roof, and then there's four walls of some sort. And that's what defines the building enclosure, the building envelope, so on and so forth. For complete building airtight layers, you cannot have one without the other. Okay, I'm getting a note that there may be a bandwidth related issue. Maybe just give me a quick second. I'm going to change my Wi-Fi port. Okay, I'm going to keep rolling. Hopefully that works a little bit better now that I switched over. If whoever is in the chat could just let me know if we're getting any better or we're staying the same, that'd be great. So again, for containing our conditioned space, you have to have the combination of an airtight layer and an insulated layer. That's what defines conditioned space. Our building envelope basically encloses conditioned space, and that's the area that's being heated and cooled. Right now, I'm really happy to have air conditioning. Historically in Michigan, you might have been able to get away without air conditioning. I wouldn't want to be living here in Metro Detroit without air conditioning right now because we're going through a major heat wave, as is much of the rest of the country. So things that are within the home that tend to be conditioned space, bedrooms. I'm working out of my office right now. That's definitely conditioned space. Kitchens, bathrooms. These are all primary living spaces, and we tend to have them within our building thermal envelope. We tend to have them as conditioned space. Sometimes we may have spaces like attics, basements, or crawl spaces as conditioned space as well. In Michigan, I would say basements are almost always conditioned space, either directly conditioned or sometimes sort of like semi-conditioned. The mechanical equipment and ductwork maybe lives in the basement, and our pressure boundary and thermal boundary may be at those foundation walls. Other parts of the country, you'd be surprised, like the Northeast tends to have a lot of unconditioned basements. And so kind of an interesting thing here in Michigan, we don't really deal with that. We pretty much have almost uniformly conditioned basements. Attics, I would say generally speaking in Michigan, are vented, unconditioned attics. But certainly you can have enclosed, sealed, conditioned attics as well. I happen to have one for half of my house. Half of my house is sealed and insulated at the roof line, so as to open up a little bit of bonus space on my top story, and then have partially a vented flat ceiling for the rest of the attic. Crawl spaces, I would say we are increasingly moving towards having crawl spaces that are within the conditioned space. We are insulating and sealing at our crawl space walls. Not necessarily always the case, but there's a lot of benefits for sealed crawl spaces. We talked about that in the last couple webinars. We don't need to talk about that a whole lot more because it doesn't pertain all that much to fenestration. Rarely, but sometimes, garages and porches are considered conditioned space. More often than not, they are unconditioned spaces that are not part of our building thermal envelope. So kind of focusing again, we had to set the stage for what we're trying to define. This is the last series about the building thermal envelope, talking about fenestration. So as it pertains to fenestration, it's a huge part of making or breaking a home in terms of energy efficiency and comfort. The selections that are made when it comes to windows and doors can have a dramatic impact on whether or not people feel comfortable in their homes, whether or not they have the connection to outside space that they desire from an aesthetic standpoint. And it's really important to understand that not every window is created equal, and that I would say the more that I've gone on my career and learned more about sort of the performance of fenestration, I've learned that there's actually a lot more to it in terms of the proper design, installation, selection that goes along with the full consideration of the application of fenestration within the building envelope. It's not just about the NFRC sticker. And it's not just about what looks pretty. So we'll get into kind of all those details here. So when it comes to fenestration, we're really talking about windows, doors, and skylights. And the key factors that influence building performance are really kind of these four factors that we do see on the NFRC sticker: the U factor, the solar heat gain coefficient, the air leakage coefficient, and the visible transmittance. And so before we kind of dive into that NFRC sticker and kind of mince each of these individual ones, an important and really critical thing for you to think about is no matter what the NFRC sticker says, windows in general are not great for the building envelope. And why do I say that? Well, a standard code window is about an R3. Why do I say that? Well, because a standard code window might have, well, here in Michigan, the minimum code value is 0.32 prescriptively. So we can take that U factor, 0.32, and we can take 1 divided by that 0.32, 0.32, and that basically gives us an R3 as an average. So, and I'm equating it to R values, even though we don't use R values so much in the parlance of discussing fenestration. Usually we're talking about U factors, but I'm doing it for a reason here. So just follow me. So, a standard code window is an R3. The best you can really get there out on the marketplace in a very high performance triple pane or maybe even a quadruple pane window would give you about an R10. So that, that's pretty cool. Wow, we can get 3 times better essentially than a standard code window. That's awesome. That's great. But if we compare that to our R20 walls that we might have prescriptively, well, all of a sudden, a standard wall is 2 times as thermally resilient as the best possible window that you can get. So I say all this to draw the fact that in general, windows are losers. You're generally going to have more heat loss when you add windows to a building than if you don't. And there's more of a chance that they leak air, and there's a chance that they leak water when we cut them into our wall assemblies and other parts of the building envelope. So it's not to say don't install windows. You need them. You need them by code. There's a certain amount of minimum glazing area that's required by code. People like windows so that they can see outside and get a touchstone with the outdoors, daylighting purposes, ventilation in the optimal season. Everybody likes windows for the most part. We need to have them. We do build them into our homes, but in some ways you could say less is more, or we at least want to optimize their utilization in the building, because even if you get really great windows, they're still going to be insufficient from a thermal perspective compared to just our standard opaque wall assemblies. So let's just install and build homes without windows. Well, all right. The problem with that would be we wouldn't have that touchstone outside. Right now, I'm able to casually look out my window adjacent to my office desk, and I'm able to see the leaves on the trees, and maybe a squirrel or a bird outside, and that's really great. I like that feeling. I'm getting a little bit of daylighting coming in. Right now, I have just a small task light on inside my office. And aside from that, I don't have any other light that's on. I'm able to see because I have daylighting that's occurring. Right now, any solar gain that's coming through the windows, that would be detrimental. I wouldn't want that solar gain. Why? Because it's 90 plus degrees outside, and any amount of solar gain that comes through the windows means I have to pay with air conditioning in order to get rid of that heat. So we want to be careful about that. We've got a participant that just said all of the shades are closed so that he can block out all of that solar gain that may be coming in. And that's not a bad idea, to be certain. The other pro of windows is that in the optimal season, we can use them for ventilation and even a little bit of free cooling for that reason. So not today, and maybe not for the next couple of weeks, because boy, is it hot and humid, at least here in Southeast Michigan. But let's imagine that it is a September evening and it was kind of hot during the day. And then in the evening, it starts to cool down and we're kind of in like the 60s outside. Well, we can open up our windows and get free cooling through those windows, and as well as a lot of fresh air coming in through those windows. So that's really beneficial. We need windows for that reason, or we certainly like to have them for that reason. Finally, you need them as a point of egress. You need to have windows in homes just in case there's a fire or some other kind of emergency so that people can escape. So we can't really build homes without windows. That would be problematic for a lot of reasons. The challenge with windows, though, cons, again, especially today, if I've got, my windows on the south side of my home, if they're not shaded, then they're just taking in a lot of solar gain right now. And that is heating up my home. And I'm going to have to end up basically paying to condition all that solar gain out because it's overheating my home. Windows can also be very leaky. Up until 2 weeks ago, I had original single pane windows with storms. I just went and replaced my windows. It's very timely that I'm speaking to you all on the topic because I know a lot about this whole topic nowadays. But my home is now much more airtight because I replaced my old leaky single pane windows with modern airtight windows. Makes a big difference. Energy loss, so again, my single pane windows were with a storm, you might say a single pane window with a storm. A single pane window by itself is like an R1. A single pane with a storm is maybe closer to an R2 if you use that storm window. Well, I ended up getting windows that are closer to an R5. And so I'm doing a lot better in terms of reducing conductive heat loss through my windows. Moisture, because my windows are more airtight, I also am not bringing in humidity from outside. And in the winter, I won't feel draftiness if the wind is blowing or if there's a big temperature difference, which drives the stack effect, something we talked about last week. Then having better windows are going to end up basically reducing those drafts. But again, all windows leak to some degree. All windows have some amount of air leakage. All of them are going to bring in some amount of moisture. They're all going to lose some amount of energy compared to walls. And they will all bring in some amount of solar heat gain, which may not be advantageous during some parts of the year. These are the pros and these are the cons of windows. So it's not to say don't put them in the home, but we got to be thoughtful about it. So thinking about the design of windows is critical. They can bring in daylight that can provide useful heat in the heating season, as well as potentially useful ventilation for maybe free cooling and just decent air quality if selected and installed properly. So that's what we're trying to get you to, is how can you think about this? I think a lot of people, when they get into building a home, it's kind of like, well, I want to buy the window that looks the best. I mean, fair enough. I get that. I mean, I think that a lot of things in the world of construction come down to aesthetics, but you don't want to sacrifice performance just off of aesthetics. And I will also say, just because you get a better performing windows, it doesn't have to cost more either. If you shop around and you're thoughtful about the window selection for your home, you may turn out that it's closer to budget neutral than what you may have actually anticipated. Especially people who are maybe building higher end homes or custom homes. I hear people, I don't want to talk about any particular brand, but there's a big brand out there in the sort of the higher end custom home market. It begins with an M. That's as much as I'm going to give you. People love to use the M brand because why? Well, because it's got a good brand recognition. And there's a lot of options for occupants to be able to choose different customizations for the aesthetics of the windows. Okay, that's cool. I tend to find that those windows tend to be pretty pricey. And from a thermal perspective, like the performance values, they're just okay. You can get good ones, but man, you're really going to pay for it. There's a lot of other options out there. Man, thousands of brands of windows. In some ways, it's almost overwhelming how many window brands are out there. But you can get a really good window that doesn't necessarily have to cost a whole lot more, and you can get one that looks good as well. So just shop around, word of the wise. But all right, quick poll question, our first one of the day. What's the primary reason windows are considered energy losers? So we're going to go ahead and pop that poll up here. Why are windows considered to be losers? This is great. We got people jazzed to participate in this. We got people participating right out of the gate. I've got almost 100% participation here. I'm really excited. Can we get there? I'm going to call it here in 4, 3, 2, 1. We got 100% participation. That's awesome. I'm glad to hear it. Glad to see it. And everybody got the right answer. In general, windows, they have a worse performance than walls. The only time that wouldn't be the case is like if you were putting in a really good window in like an uninsulated wall, which that's not necessarily what we're trying to do, right? That's in the building performance field. That would be a practical sin. We would generally not want to sell people R10 passive house quad pane windows to put into an uninsulated 2x4 wall in a retrofit scenario. That doesn't make a lot of sense. So yeah, in general, windows are losers. Doesn't mean that they can't be selected appropriately. So how can we go about selecting appropriate windows? So first thing we want to do is take a look at the NFRC values. I think that's a good starting point. I've come to realize that there's actually more to it than just the NFRC sticker. Trust me, I haven't gone through purchasing windows and kind of going through this process. There is more to it ultimately than just the NFRC values, but it's important to understand these NFRC values because they do help to, I'd say, really illustrate better what you may be getting, and you can compare apples to apples from a performance value. And NFRC, that's the National Fenestration Rating Council. So this is like a third-party body that rates windows, fenestration products for their performance values. And these are the 4 key variables that are on those NFRC stickers: U factor, solar heat gain coefficient, aka SHGC, the visible transmittance, aka VT, and then the air leakage coefficient. They also do look at a condensation risk potential that they don't tend to publish on the sticker, and we will talk about that. So first of all, let's talk about U factor. That's the first item. And up here in the top right, we can see that U factor is the inverse of the R value. And so 1 divided by the R value gives you the U factor and vice versa. So that's why I said a code window of 0.32 is about an R3. Why? Well, because I said 1 divided by 0.32 gives us, in essence, R3. So we can kind of functionally talk about windows relatively in their R value, but they are rated for their U factor. And so it's the whole window that is rated for the U factor, as well as the solar heat gain coefficient. All these values, they're the whole window. So it's not just the glass, it's the glass. So the thickness of the glass and the number of panes, and then like the actual sort of geometry of how far spaced out those panes are. The framing characteristics, so are they wood frames? Are they vinyl? Are they fiberglass? Are they aluminum? Are they some other kind of metal? And are they filled with foam or some other insulation product? And this is really important because most people don't think about this, but what's the more insulating value of a window when you have a window that has multiple panes of glass? Is it the glass or is it the frame? Most people would say, well, it's the frame because glass seems like it would be inherently a loser. But the issue when you have multiple widths of glass is then you have a trapped airspace. And oftentimes that airspace is filled with an inert gas like argon or krypton, which further reduces heat loss. So it actually turns out that the glass is more insulative than that frame material almost always. Almost always that's the case. Wouldn't be the case in a single pane window most times, you know, but if you have double pane or triple pane or quad pane windows, then that glass is always going to be more insulative than the framing. The glass widths are spaced with a spacer product, and that spacer also factors into the performance of the window. And so sometimes they're more of like a foam type of spacer. Sometimes there are different types of metal spacers. Some are more conductive than others. So that spacer makes a difference as well. The chart that we have here in the bottom right is showing us different window configurations and ultimately what is sort of the rub on the window performance. And so it looks like we've got various types of double pane windows is what we have here. And this is really important, people. Windows are not all created equal. Just because you get a double pane window doesn't mean that it's going to be necessarily energy efficient. And just because you have a triple pane window doesn't mean that it's necessarily better than a double pane window. So it's the combination of all these values that go into it, because you could have a double pane window that has no inert gas in it, so no argon or krypton, and it has like a steel spacer that's highly conductive, and the frame is a metal frame. Well, wow, you would have actually a pretty bad double pane window in that instance. So what this chart sort of shows us here is that like the left side is outdoor conditions. So we've got cold outdoor conditions. It's 3 degrees outside basically. And based off of the different performance characteristics of the window, the indoor temperature, let's say it's 70 degrees indoors, because that's how we like to keep homes. The different characteristics of that window will end up impacting the indoor surface temperature of that window. So again, let's just say we got a metal framed, no inert gas, poor spacer, double pane window on the far left. that's why we see when it's 3 degrees outside that inside face is only like 40 degrees. Wow. Well, what's the problem with that? Well, the problem with that is that's going to be pretty cold for one. And then the other issue is that could lead to condensation issues. We could have, depending on the relative humidity inside the home, we could have that glass be a condensing surface that ends up really negatively impacting not only comfort, but also leading to condensation. Incrementally, we're improving the window, it appears. Take a look at the frame though on the far left. The frame's even worse. The frame's down to 30 degrees. So, and some of that's buried in the wall assembly. So wow, we may be condensing moisture inside the wall, and it's soaking into our insulation. Man, that's not a good thing. So incrementally, we're improving this window. Let's say we're changing the overall glass geometry in the next one over to the right. Well, now our glass surface temperature is closer to 50, warming up a little bit. Still, our frame is not very warm. Okay, now we're going to go ahead and add an inert gas. And so our frame overall, our window glass is performing better. It's up to 60. That's maybe passable. There's a couple cold spots still, though, where it drops, especially closer to that spacer. And so now let's go ahead all the way to the far right, and we're going to add a good spacer to that window. Now, all of a sudden, the glass is pretty warm uniformly. We don't have super cold spots. There's still a little bit of heat loss there, though, at that where the frame meets the spacer. So we got to watch it. Got to make sure our indoor relative humidity levels are better. Long story short, all of these values that go into basically defining, how the windows are constructed go into influencing the overall performance of the window. And so continuing on with U factor, how many panes of glass do we have? Single, double, quad? Is it a single pane with a storm window, which essentially acts as a double pane window? What's the frame? Wood, vinyl, fiberglass, aluminum. These are all typical. You can also have just like straight metal windows. Not too common around these parts, but in a lot of existing homes, like my home had some steel single pane windows. The frame was steel, and the windows were a single pane of glass. It was thicker glass, but still it was highly conductive. I ended up trading those out for these modern R5-ish type of windows, and I'm very happy that I did so. So we see sort of relative performance of different types of windows here. I'll say this chart, could be updated a little bit because I got my double pane value. I ended up choosing double pane windows. Why? Because I could get a 0.22 U factor out of a double pane window, and therefore I saved money versus a triple pane window, but I got better performance. Again, it pays to shop around and compare these values on NFRC. But it's interesting, a double pane window is not necessarily a whole lot better in its worst construction than a single pane window with a storm. So that's why it's really important, especially in existing homes, buyer beware, what you're getting, because if you already have single pane windows with storms and they're in decent shape, if you get sort of the lowest performing window or one that's not rated by the NFRC, you may not actually be improving the performance all that much, really, by going to just a standard, not so great double pane window. The other thing is, again, triple pane windows, they sound really sexy. That sounds great. Wow, I want a triple pane window. It's going to be a whole lot more comfortable. It's going to save money. Not necessarily. There are triple pane windows they're good. You're not going to get a bad triple pane window, but they're not necessarily going to be a whole lot better necessarily comparatively. And you may say, well, why is that, Chris? That doesn't make any sense. I'm adding a whole other pane of glass, a whole other trapped airspace. Shouldn't it absolutely be better? Well, again, let's go back to here. There's different characteristics that impact how windows perform. It's the thickness of the glass. the spacing of those glass panes. So how much of a trapped space do you really have? The frame material, the spacer, those inert gases, they all influence it. So just because you have triple pane windows doesn't necessarily mean that they're going to be better than double pane. So I highly recommend people shop around in order to find your best value. Solar heat gain coefficient, that's the next major value. And so the way this works is that the lower the solar heat gain, the lower the solar heat gain coefficient, the less solar gain we're going to get through those windows. And I think that there's sort of this, there's a degree of miseducation, I think, within the energy efficiency field that just getting the lowest SHGC is going to be the best. Well, it'll cut down costs in the summer. That's great. Who doesn't want to cut their electrical bill in the summer? Sure. Okay, but the problem is here in Michigan, even though it's pretty hot and humid right now, we have dramatically longer heating season where we need to heat homes than a season where we have to cool them. So having a higher SHGC can actually lead to more free heat, passive heat that comes into our homes, which can be useful. So I'm challenging you all in your knowledge to believe that just lowering the SHGC is necessarily for the best. The way that windows are able to get lower SHGC, and interestingly enough, these low emissivity coatings actually do affect U factor as well, is that basically, the outdoor light can be basically blocked depending on the location of the low E coating. So on the right-hand side, we see one that's optimized for summer. That low E coating is on the inside face of the outside pane. The way that emissivity works is emissivity basically reduces the conductance basically of a surface, the rate at which heat energy is emitted. So by having a thicker low E coating on a certain pane, basically you're going to reduce the amount of emissivity. So the solar gain is still hitting that window, but how much is allowed to pass into the home is retarded by these low E coatings. And then for the left side, if we apply that low E coating to the inside face of the inside pane, then basically our heat from inside of our home will not emit to outside through that low E coating. So again, the low E coatings affect not only SHGC, but also the U factor of the windows as well. Again, there's a trade-off between U factor and SHGC. I don't want you to walk away from this webinar thinking that all we need is low SHGC windows in Michigan because they're going to reduce space cooling. Why? Because there's more to it here. In Michigan, we are a heated dominated climate. Some heat gain is useful. It's positive. It can be used for a beneficial reason here in the state of Michigan. We are in climate zones 5, 6, and 7. We are a cold part of the country overall. So having some free gain coming into our homes can be very beneficial for providing free heating of the home. So again, I said that the low E coatings can impact both U factor and SHGC. And in fact, this is what I've found in my research going to buy my own windows for my home was that a lot of windows are achieving better U factor performance by just adding thicker low E coatings. And so they're driving down the U factor by adding these low E coatings, but in doing so, they're also driving down the SHGC. And so again, we get some beneficial heat from SHGC in this climate. And so it's not necessarily always the best to select a window that just has the lowest U factor. You may want to balance a lower U factor with potentially a higher solar heat gain value in order to optimize the amount of solar gain that can be brought into the home. Now, A lot of that depends on the other things. What's the orientation of your home? How many square feet do you have on different sides of the building? If it's on the northern side of the building, well, guess what? The sun don't shine on the northern side of the building. So you're not going to get any free heat. So if you have a northern oriented home with the dominant amount of glazing on the north side, go for the lower U factor. But if you have more of a southern exposure with more windows on the south side, it could be advantageous to have a higher solar heat gain in order to bring in that free heat and passively heat the home. Interestingly enough, there is a relationship between solar heat gain coefficient and visible transmittance. VT, I think a lot of people in the energy efficiency industry don't even know or think anything about visible transmittance. It's actually really kind of an important value. So visible transmittance basically helps to provide daylighting into our homes. It's how much useful light comes through the window in order to provide daylighting. And it can impact how sort of our connection to outdoors feels. When you have a lower visible transmittance, that's oftentimes going to result in almost like a green or grayed out type of view profile. So it's going to be like you have tinted windows. And so it's not, the colors that you see from outside are not going to be nearly as vibrant. And so the challenge is, especially here in a colder climate, oftentimes window manufacturers, I'm finding, is in order to get better U factor performance, they are applying thicker low E coatings to their windows, which therefore reduces the U factor of the window because we have less emissivity off those windows, therefore less heat loss off of those windows. That sounds great, but when you add those thicker low E coatings, it also affects your solar heat gain coefficient, and it tends to lower that solar heat gain coefficient. And then when you have a lower solar heat gain, that typically means lower visible transmittance. So again, here in Michigan, if we just go and select the window that has the lowest solar heat gain coefficient, because we heard that lower SHGC is good, it will save on cooling costs. The consequence is you may end up reducing the quality of light and the quality of views that you're getting through those windows, which again, that's one of the main reasons why we have windows to begin with, is so we feel that connection to outside. So I'm just cautioning here that there's a lot more to the story than low U factors or low SHGC. You would want to consider something like visible transmittance. So when I went to go and buy my own windows here recently, the initial quote I got was from a colleague that sells a decent and somewhat affordable triple pane window. It's not like a super high performance German passive house window. Why? Because these are retrofit insert windows. It just wasn't practical. They don't really make that style of window for an insert type of condition. Well, the U factor performance was great on these windows, but the solar heat gain was like really low. And looking out the windows, like they brought over a sample and I put them up next to my existing windows and it looked very green. It just, the quality of light wasn't good. So I ended up not going with that triple pane window, and I found a double pane window that performed just as well in terms of U factor performance, but with a modestly higher solar heat gain value, and more importantly, with a better visible transmittance. And so I'm overall a lot more satisfied with my windows because I was a little bit more thoughtful on how I selected them, considering all of these values that go into affecting sort of the quality and performance of the window. Air leakage coefficient, that's another reason. The window that I ended up getting, the industry standard is 0.3 CFM of leakage per square foot of window area. The ones that I went for were 0.03. So they were 10 times tighter than the standard industry rating on windows. And, you know, look, I don't want to have an air leaky house. Again, I don't want drafty windows. I don't want more humidity coming into my home. The other thing too is that when you have better air leakage coefficient, you're probably going to have better sound performance. I live in Detroit. It's an urban area. You got people who are using lawnmowers and leaf blowers and driving their cars somewhat fast. And man, that all makes a lot of noise. Since putting in my new windows, it's a lot quieter in my home because they're more airtight and better insulated. I would say the air leakage coefficient that's rated by NFRC, that's not the only deal. It's also about the installation. So when my window installers were putting the product in, they started chinking in fiberglass around the rough opening. I said, you guys that's fine if you want to do that, but you also have to seal it with foam. Why? Because I wanted to make sure that the windows were airtight on the outside. Because we can have an awesome product from the factory that doesn't leak, but then if the rough opening, which is roughly about a half an inch all around the perimeter of the window, if that's allowed to leak, well, all of a sudden we're going to still have air leakage, we're going to have draftiness, we're going to have comfort issues, and so this kind of just gives you a little bit of an idea here. These couple of thermal images were taken that show basically during a blower door test, an infrared thermography photo that's showing air leakage coming in, not from the window itself, but around it. Basically that, those windows were installed and they're still leaking air into the house. Not good. But if we just go with like a standard 15 square foot window, a 0.3 CFM out of the box, that's 4.5 CFM per that window, you may say, well, that's not such a big deal, but if you have, 500 square feet of them, wow, you're already adding up. That's about 150 CFM just from the windows. And that's if they're perfectly installed. For me, I got the 0.03. So I'm down to about, 15 CFM leakage from my windows, ideally. The NFRC sticker is one thing that, well, of course, we know that there is an Energy Star program in this country still today. We'll see about tomorrow, but Energy Star has, programs for buildings, and that's primarily what we've been talking about in this series is basically the performance of windows for different programs like Energy Star. But there is actually an Energy Star window rating program as well. It's important to understand that this changes over time. So like, our current window specs for a northern climate, prescriptively, you'd have to get a 0.22 U factor with greater than a 0.13 SHGC, and that would comply basically. So that's kind of what I have. I've got 0.22 windows, and then my SHGC is somewhere in the high 0.2s to the low 0.3s. If you get worse thermal performance, so worse U factor, then all of a sudden you have to have higher solar heat gain coefficient in order to make up for that. That's kind of how this works. And then there's an Energy Star most efficient category, which would require basically R5 or less with a SHGC above 0.2. So my windows are Energy Star. They are not the most efficient category because they are not below that 0.20 value. Another quick question. Where does most window-related air leakage usually come from? Through the glass, through the sash, around the rough opening, or between panes? Let's go ahead and fire this up. Poll question. Let's go ahead and put that poll up here. Okay, all right, we're going ahead. We got people answering it here. Let's get some participation here. We've got a couple folks that have weighed in. All right, people, let's go. Let's get in on this poll. I'm going to go ahead and move on in 5, 4, 3, 2, 1, ending the poll. And I appreciate everybody's participation who did. Around the rough opening, that is correct. That is where most of the air leakage will occur in a window, is around the rough opening if it is not installed properly. Radiation and thermal performance. So again, the surface temperature makes a big difference, both in terms of comfort as well as the risk of condensation. So if we go back to that colorful image that showed sort of the potential heat loss off of different configurations of a double pane window, we saw that some of them had like a indoor temperature of like 40 degrees. Well, guess what? That's going to feel like a draft. It's going to be sucking heat off of our bodies being close to a cold window like that, and it's going to feel like a draft. The feeling of draftiness near a window is usually through radiation, heat being sucked off of our bodies rather than air blowing. Could be a combination of both. But the other issue with having those reduced surface temperatures is it can cause condensation. Basically, if we have higher relative humidity in our homes and we have a cold surface that can hit the dew point value, can cause moisture to actually bead on them. That's why we tend to see moisture on windows. Other considerations beyond NFRC, the amount of windows. Again, in general, windows are losers. So having higher window to floor area ratios are going to end up impacting, our energy performance. Orientation matters. We get light that comes to us through the southern exposure because we're in the northern hemisphere. And so we tend to get solar gain that will come through the east, through the south, and the west. Shading and overhangs matter. And then the condensation risk. So again, window floor area, choose the right amount. Yeah, everybody wants views, but if you have too much glazing, then you're going to end up wasting a lot of energy. So be thoughtful about the design and optimization of the amount of windows that you have. Really, less is more. Orientation. Typically, north is not the best place for a lot of windows. Why? Well, because we're not getting any beneficial free heat coming in, and we just get a lot of heat loss, basically. The south side tends to be better in colder climates because we can have passive heating potentially. East and west, you get a little bit of a benefit there, but especially if you're loading up your west, that's where the sun sets in the west. And so imagine you're got an open floor plan with a kitchen and a living room, and you got a bunch of people hanging out in summertime, cooking inside the kitchen and hanging out in the living room. And then you got a big gang of windows facing west where you're going to be really solar loaded in a way that's potentially going to cause comfort issues, maybe even in the wintertime. So you have to be careful with that. Overhangs make a big difference. You can design overhangs that allow heat to come in the winter when the sun is lower in the horizon, and then basically block out the sun when they're higher in the horizon during summertime. So having purposeful overhangs for windows can actually be a very important strategy for maintaining comfort of the home. Other things can provide shading, though. Adjacent shading. I happen to live in a neighborhood that has lots of old verdant trees. And so I get a tremendous amount of shading on my windows from adjacent shading features as well. Passive solar design, again, the optimization of window area overhangs, solar heat gain coefficient, usually tied to the south of the building. So you can bring in some beneficial heat in the winter and then block it out in the summer with appropriate overhangs. You can also store some of that solar heat in things like thermal mass. So if you have like a slab floor or a tile floor, anything like masonry that is able to store heat because it has higher thermal mass can be advantageous for a passive solar design. But you want to be careful. You don't want to overheat the house with too much passive solar heat. Condensation risk. Again, NFRC rates windows for condensation risk. Basically, in essence, the higher the R value or lower the U factor, in general, the condensation risk is going to be lower. But I will say that where the low E coatings are in the windows, and some of the other values like the ratio of frame and the spacer material, that can also impact it. So it's not necessarily always as simple as the lower the U value, the better the condensation performance. There can be some nuances where that's not necessarily correct, but in general, better thermal performance is going to lead to better condensation risk mitigation. Doors. Well, doors are another fenestration product. A lot of them are basically going to be pretty standard that come from a R5, R6 kind of profile. That's, sort of steel insulated doors or wood or fiberglass sort of clad doors. Anything that's over 50% glazed is really rated more like a window. So we tend to not have that many doors in a house, and when we do have large door areas, it tends to be because they're glazed doors, and you should really think of them more like a window. Okay, windows located on which side of the home will typically result in the lowest cooling load? Okay, let's go ahead and fire up this poll here. And we're going to go ahead. Which side of the house is going to have the lowest cooling load? I've got one person participating. Let's get on it, folks. Jump on this. I want everybody to participate. Fill out this poll. We are trying to get here to the finish line, but I need people to participate. We're going to give it 5 more seconds. 5, 4, 3, 2, 1. All right, and we're stopping the poll and sharing the results. Not a ton of participation, but the north wins, and that is the correct answer. The south side of the house, you could actually have a very high cooling load on the south, depending on your shading, your overhangs, and the solar heat gain coefficient. The north side practically gets no sun coming in through the windows, and so you're not going to have much cooling load from northern facing windows, but you will have a lot of heat loss off of them. Okay, jumping into windows in code. Michigan's energy code prescriptively requires a 0.32 U factor and has no requirements for solar heat gain coefficient. Why? Because we are in a cold climate and solar heat gain coefficient is not regulated. There's a small amount that can be sort of exempt from this for a decorative value, and you can do area weighting of U factor. So, you could have better performance on one side of the house and worse performance on the other side, and that would still work out. You can also do a total UA value, and that will work as well for the total house. So you could potentially trade off worse windows for better values in other parts of the home. If you get into doing performance code, as many homes do in Michigan, there's no regulation on the amount of windows or what U or SHGC you have to use, but it's useful to understand that the reference home has 15% window to floor area ratio, basically, or equal to that of the proposed home. So if you exceed 15% window to floor area ratio, you're going to end up having to basically make it up somewhere, because as we know, more window area is not necessarily better from a thermal perspective. They have equal orientation as well. So if we have 400 square foot of windows, basically the reference home would have 100 square feet on all 4 sides. And the reference home has a higher SHGC value, which again can be advantageous for this climate. If you're using the ERI performance method, there really is no windows specific requirements. Basically, you have to meet at least the building thermal envelope performance using the total UA method of the 2009 IECC. Not a big deal. Above code programs. So jumping into a HERS index score, and we've talked a lot about HERS index scores in previous presentations. There's no specific requirement. And that's the beauty of HERS, is that really it gives builders ultimate flexibility about how they approach energy efficiency of the home. That being said, it's important to understand that the reference home has basically 18% window to floor area ratio. So if you had really significant glazing, you would end up having to make that up on the HERS index. But if you have lower window to floor area ratio, you actually gain some benefit on the HERS index calculation. Orientation, SHGC, U factor, those are all factored into it. Visible transmittance is not factored into the HERS rating, but it may have a quality of life impact. Air leakage coefficient is not directly related to it, but leakier windows will impact your blower door score. For Energy Star homes, For version 3.1, which is the program that is required for participation in DTE and Consumers New Homes program, we have to meet version 3.1. And that just requires a total UA compliance for the whole building equivalent to the 2009 IECC. Again, windows are part of that consideration, but so are walls, ceilings, floors, etc. So you have enough wiggle room there. If you get into version 3.2, which is what's required for the current version of the 45L tax credit, well, now you're looking at basically having to meet the 2021 IECC total UA, and that is a little bit more challenging. Interestingly enough, Energy Star certified windows are not required for certified homes. It's not required that you have an Energy Star window in an Energy Star home. That's sort of a misnomer that people have made the mistake of. If you get into Energy Star Next Gen, same thing, version 3.2 it basically is what is required for the lay of the land. If we use version 3.3 of Energy Star, there is a little bit of a trade-off. We can be 115% of the total UA value of the 2024 IECC. Okay, true or false? I'm going to skip the poll here because we just don't have enough time for it. Energy Star windows are not required for Energy Star certified homes. So it is false that you have to have an Energy Star certified window in an Energy Star certified home. Okay, zero energy ready homes. There are minimum window performance values that are required for zero energy ready homes. Basically, we would have to have a 0.27 U factor with any SHGC, or potentially a higher U factor with a higher SHGC to make up for that higher U factor. But nevertheless, we still have to be better than code for any of these window configurations. When you get to climate zone 6, 7, and 8, which is sort of north of Clare and getting into the UP, we have to have basically at least an R4 window with any SHGC value. So there are some kind of hard requirements here for zero energy ready homes. Again, there are a couple of exemptions, higher elevation areas. We don't have to worry about that because we are not in a higher elevation area here in Michigan. Passive house tends to have much better windows. We tend to have higher SHGC values for free heating in passive house. There's more of a focus on proper orientation, and then really optimizing the amount of windows and probably reducing the amount of window area overall. You know, and the U factors tend to be a lot better. This is the prescriptive value for FIAS. So in climate zone 5, basically around an R6 window, and getting into climate zone 6 and 7, like an R7-ish window is what is required in order to meet the prescriptive values. Now, you can trade those off with the performance method as well, but this kind of gives you an idea of some of the ballpark values when you're getting into passive house. And again, we're going to have whole sections of this webinar series on passive house later on. This is an idea of some of these super high performance windows you may see. You know, you could get R10 quad pane windows, super low air infiltration, and the visible transmittance and the SHGC vary. You know, this is a side profile of some of these really super high performance windows, really good high performance windows that have very low overall U factor. And again, the solar heat gain coefficient can vary. I mean, some of these, honestly, solar heat gain coefficient is kind of low. Again, you got to be careful. Maybe now we're not going to have very much visible transmittance coming in through them. But you get an idea here of at least how high performance windows like this may be constructed. Okay, so we are a little bit over time. I apologize for that, but you could just tell I had to nerd out about Windows. I learned that there's so much more about Windows that goes into it than what I think the average person assumes. Stay tuned for next week's series on air distribution systems in homes. We are going to be taking a week off, so the next scheduled of these webinars is going to be July 8th. So stay tuned for that, and we will see you then. Take care.